In this section, we'll put together a lot of the things we've already talked about. So Theorem 8 is the invertible matrix theorem, and we have looked at pieces of this. And so let me just emphasize that when we're talking about A, we're talking about a square matrix A, so it's the coefficient matrix. And we know that if A is invertible, then all the rest of these things are true. If you know any one of these things is true, then all the rest are true. Also, if any of them are not true, then you know the opposite of the others are not true. For example, if you know that A does not have n pivots, then that means you know that the columns of A do not span Rn. So you can put knots in front of them, they're all the same. Just to emphasize, all of these will be on this next test, except for this one that talks about being one-to-one, and this one talks about to be onto. So one-to-one and onto, we just won't really touch on. I might mention it here and there, but it will not be on the test. I also would like to emphasize G. So sometimes instead of that phrase, it says the equation ax equals b has at least one solution for each b in Rn. It really could say ax equals b has one unique solution for every b in Rn. And we will add more to these in later sections when we learn about determinant and other things. So we will be adding to that theorem. But that kind of summarizes what we've done so far. So in this first exercise, each statement is structured as an if statement 1, then statement 2, and we're going to just see if it's true or false. So if A is square and has a pivot position in every column, then the columns of A are linearly independent. So let's just think about that. If it's a square and it has a pivot in every column, that means every row also has a pivot, then A is linearly independent, and that is true. Part B says if A is square, then the equation ax equals b has a unique solution given by x equals a inverse b for each b in Rn. So according to the theorem, ax equals b has a unique solution given by this x equals a inverse b only when A has an inverse. So you need to say if A is invertible, then that's true. So just being square is not enough. So this is false. Part C says let A be an n by n matrix, another way of saying square. If A has fewer than n pivots, then the linear transformation x to ax is not one-to-one, nor does it map Rn onto Rn. So strictly looking at the invertible matrix theorem, this is true. It uses C, F, and I. So it said it did not have n pivots, then it is not one-to-one, and it is not onto. In exercise 2, we're going to look at some different matrices, and I just want to determine, is the matrix invertible or not? And you can really use any of those ideas that we saw in that theorem. So if I just look at the columns of this matrix, I can get from column 1 to column 2 by multiplying by 2. So I'm going to say notice columns are linearly dependent, so A is not invertible. In this next one, I don't see any immediate relationship between the columns. So I'm going to row reduce it a little bit, see if I can make some observations. So I have 1, -5, -4, 0, 3, 4. To zero out this -3, I'm going to add it to 3 row 1. So I have 0, and then 6 plus -15 is -9, and then 0, -12. And if I keep going, I have 0, 3, 4, And then if I divide the last row by -3, I have 0, 3, 4. And I know that I will only have 2 pivots because I know this last row will become all zeros. So 2 pivots in a 3 by 3, so not invertible. In part C, I see I have a column of zeros. There's no way that I'm going to get a pivot in that, so you could say there's only 2 pivots. You could also say the columns are linearly dependent. Lots of different things you can say, but A is not invertible. In this exercise, we're given first a definition. Upper triangular matrix is a square matrix whose entries below the main diagonal are 0. So I'm going to say upper triangular. So you have the diagonal entries, whatever they may be, and the entries below are all zeros. And a lower triangular is kind of the opposite. So you have your diagonals and your 0 above. So upper referring to there is stuff in the upper part, and lower meaning there's stuff down here. I'm just put stuff numbers. And if you are either upper or lower, you are considered triangular. So thinking about a triangular matrix, we want to think about when is a triangular matrix invertible. So if we have, I'm just going to think about a upper triangular matrix. I can see that I will have 4 pivots. So because I have 4 pivots, I know that this is invertible. And if I just changed one value, maybe if I change this to a 0, now I only have 3 pivots. So as long as my diagonal entries are non-zero, so if diagonal entries are non-zero, then the triangular matrix is invertible. Exercise 4 asks, can a square matrix with 2 identical columns be invertible? So if we have 2 identical columns, that means these 2 columns are dependent. And we'll say no, because columns would be linearly dependent. Exercise 5 says, is it possible for a 3 by 3 matrix to be invertible when its columns do not span R3? Well, if the columns do not span R3, that means one of them is dependent on the others, and the columns would be linearly dependent and thus not invertible. So I'm going to say no, because the columns would be linearly dependent.